to talk about. So I think that Joe Bales, back in the early days of concocting our list of topics for Physics X, I'm just not even going to try and rein you guys in today. I'm just going to go ahead and give up. And I think I'm going to ask, oh, let me find it.
It's six, or isn't it?
I'm going to put away all the cards but one. Anytime I have a question, I'll come over and pick up the card, but it won't really be necessary because we all know that Ashley is going to answer it. Anyway, okay, so early in the days of Physics X, I feel like the light is out, but maybe I'm wrong. Early in the days of Physics X, I think it was Joe Bales asked if we would talk about the Baryon asymmetry of the universe. Were you the one that wanted that? And then we all closed our eyes and put our heads down and we voted and you got voted out. Yeah. Right?
I wanted to talk about photons.
So we didn't, oh shoot! I forgot to write down what a photon was. Okay, I apologize. If somebody will remind me next time, I'll write down what a photon is, but I can't do it today. And I can't just write it down from memory. I have to remind myself of exactly what it is. No rotating black holes today, sorry. But it's gonna be good, it's gonna be good. Okay, all right. So our first topic is, you're really dying there, is why you are matter, okay? Not so much why you matter, but why you are matter, right? And this is really interesting, and kind of putting these notes together, and people know how I slaved over this because they know how I was panicking when they wouldn't print. All right, but in putting these notes together, I kind of realized this is actually a really good topic to talk about in this course because it utilizes a lot of important themes from this material. It would be a little better suited to maybe being done the last week of the course, but we could use it as a preview for some of the things that we're going to talk about, in particular when we discuss the weak interactions in a couple of weeks. But anyway, it's a really cool topic, and one that I think many of you probably maybe have some curiosity about. So the essential question here is, if we look out in the universe, we see a lot of matter, right? Sure. But in our analysis of the standard model, we know that antimatter plays, kind of a similar role as matter. So that leaves the question of, well, why is there so much matter and so little antimatter in the universe? And so the question can often be posed as the matter-antimatter asymmetry of the universe, but typically it's actually called the Baryon asymmetry problem. And the reason we refer to it as the Baryon asymmetry problem is because when we actually look out at the abundance of stuff in the universe, okay, things that stars are made of and planets are made of and so forth, for the most part, the massive things are due to the presence of baryons. So if you don't remember, and if you have your sheet, that sheet reminds you, a baryon is a collection of three quarks. So for example, the proton is a collection of an up, and a down quark. By contrast, the mesons are a collection of two quarks, say an up and an anti-down. Okay? And you can also, of course, have antibaryons, and in this case, the antiproton would be an up bar, and a down bar. Okay? And it turns out that when we encounter quarks in the natural world, they're either always in three quark-bound states or two quark-bound states, for reasons which we'll learn when we study the strong interactions. Now, the thing is the mesons, all of the mesons are unstable and they decay very quickly. So if you just go out in nature and you look around, chances are you're not going to find any mesons anyway. Okay? Most of the baryons are unstable. There's a lot of really high-mass baryons made with various high-mass quark combinations. But the smallest two, in particular the up-up-down and the up-down-down, okay, those combinations are pretty stable. This one is stable, at least its lifetime is longer than the age of the universe. And then this is the neutron. And the neutron in an atomic nucleus is stable, but you pull it out by itself and it will eventually decay. But these are both long-lived baryons. And so when we look out in the universe, we see a lot of protons and neutrons, and those are long-lived baryons. And the other thing that we see in the universe is a lot of electrons, right? And how do we know there's a lot of electrons in the universe? Ashley, how do we know there's a lot of electrons in the universe?
Because Alex is so negative.
Yes, exactly. Because the universe is neutral, it's electrically neutral, and we know there's a lot of protons, and so there have to be as many electrons as protons in order to kind of get things to be electrically neutral. Of course, you can have as many neutrons as you want because they're electrically neutral on their own. Okay? Now, we really care about the baryonic content of the universe because the mass of even the lightest baryons, okay, the proton is the lightest baryon, the mass of the lightest baryon is hella huge compared to the electron mass, okay? So if you want to calculate the mass of a star, you can all but ignore the mass of the electrons in it and just count the mass of the protons and the neutrons in the star and pretty much get the right answer, okay? So when we're trying to take a survey of the matter that's in the universe, really the counting that we need to bother ourselves with is the baryons. And what we discover is that we see almost entirely baryonic matter and no anti-baryonic matter. Okay? So the question of the baryon asymmetry is simply, why don't we see as many antibaryons as we see baryons in the universe? Now, the very first thing that I have to point out about this, which is a very interesting part of the story, well, first of all, let's get a number because you're scientists and you like numbers. Does anybody have any idea how many baryons there are in the universe?
10^46.
So there are 10 to the 80 baryons in the universe. Okay? Yeah.
How did we get that number?
We guessed. So, no, so it comes from looking at, I mean, it's basically observational cosmology. So you're going to look at the density of clusters, the density of stars. You have a lot of information about how stars work. You can infer from their spectrum how big they are, and then infer how much mass they have. And I mean, basically take the mass and divide it by the mass of the proton or the neutron. It doesn't matter. They're close enough. And you'll get an idea of how many baryons there are in a star. And then you can look at the density of stars. And basically from that you can make an estimate. The point is it's a hella big number. And if we ask how many antibaryons there are in the universe, the answer is approximately 0. So maybe I should say both of these are approximate. Okay, maybe occasionally something is happening, an antibaryon gets produced, the whole universe is like, so what? But pretty much the answer is effectively there are 0 antibaryons, there's 10 to the 80 baryons, and so how big of a difference is that?
10 to the 80. Infinite. Big.
It's a really, really big difference, right? But what makes the baryon asymmetry of the universe so interesting, or one of the things that makes it interesting, is that this is actually a very tiny difference. Because to think about baryon asymmetry and when the relevant physics was taking place, we should not be thinking about the universe now. We should be thinking about the universe very early on. Okay? In particular, if we backtrack through the history of the universe to the earliest stages where we're kind of comfortable with our description, we can go back to about a billionth of a second after the Big Bang. And if we go back that early in the universe, you all kind of have some idea of what this looks like. The universe was very, very tiny. It still had all the same stuff in it. So if you take all the mass and energy in the universe and you get it into a really, really tiny region, it's going to be hot, really hot. It's all that energy concentrated into a region. In particular, the energy density is very high. So when the energy density is very high, you're going to be creating all kinds of matter-antimatter particle pairs because you've got lots of energy at your disposal to create those sorts of things. And what you find is that at this time frame, the difference in the number of baryons and antibaryons in the universe was 1 part per billion. That is, for every billion antibaryons in the universe at that stage, there were 1 billion plus 1 baryons. And then what happened is, once the universe started cooling, the baryons and the antibaryons paired up and disappeared, and everything we see is that 1 part per billion that was left over. Okay? Now, you might say, oh, that means it's like less of an issue. That actually makes the baryon asymmetry problem much, much harder. Because it turns out it's much easier in physics to explain 0 than it is to explain a very small number. For example, if I take Ashley, come here. I'll draw a card. Oh, it's Ashley's card. Okay, so I was thinking about how to illustrate this. So if we took a chainsaw and we cut Ashley right down the middle, and then we formed the mathematical quantity of the mass of the right half of her severed body, subtracted from the mass of the left half of her severed body. Hold on, okay? We could anticipate that difference is going to be non-zero, right? Because Ashley is not perfectly symmetric from left to right. Her heart's on one side of her body, if nothing else, right? So if we cut a person like geometrically down the center and we form the quantity of the difference in mass of the two sides, you can go sit down. We're not actually going to do this, but thought about it. But the fact that she's not symmetric explains to us that there's going to be a small difference. However, if we wanted to have the difference be exactly 0, we could say, I want a human which is perfectly symmetric. And if they're perfectly symmetric and I cut them in half, the two sides would have exactly equal mass, so if I took the difference, it'd be 0. So symmetry arguments are kind of an easy way to make things 0. To get things to be non-zero requires something a little more sophisticated. Of course, we know how it happens in biology. Biology is full of accidents, you know, your life choices, developments. So this is actually a really difficult problem to try and solve. And man, I wrote so much on this, it's hilarious. And there's a lot of like Ide's jokes that I'm not going to read and remember. No, I'm not going to say these jokes. Okay, you can read them online. Good luck. Okay, so the challenge is to think about particle physics, but you have to think about particle physics in the context of cosmology, like early universe kind of stuff. So general relativity, unfortunately, becomes an important part of the story as well. But you have to think about particle physics in cosmological scenarios, and you have to kind of come up with a mechanism that can explain this baryon asymmetry. Now, first of all, no physicist believes, rightfully so, that the universe was not created symmetric. I mean, in the Big Bang itself, there's no reason to think that the Big Bang just created one more baryon than antibaryons for every billion baryons. I mean, there's really nothing in the physics that you could, I mean, not that we understand that physics, but it's just sort of inconceivable that the universe was born asymmetric. Okay? You know, we're all born out of this singular explosion, the Big Bang. Everything came out of this point. So the way that we think about the problem is as follows. We think about the universe being born symmetric. The universe is born with the same number of baryons as antibaryons. But then at some point in its development, a point very early on probably, something allowed those two numbers to become different. Okay? So that's the framework in which this problem is typically addressed. It started out symmetric and then something allowed it to become asymmetric. All right? Now, the really groundbreaking work in this happened in 1967, before I was alive. And it was done by this physicist, Andrei Sakharov. And he wrote down 3 conditions that have to be satisfied by any process. Oh my gosh. Next spring, I'm not scheduling this class at 5. I'm scheduling general relativity at 5. Okay, so and what I'm going to do is I'm going to go through each of these conditions one at a time and explain why it's needed, and then explain at least some proposals or evidence within the standard model for how it's actually achieved. So the first thing I'm going to do is I'm going to list them, and they might not mean very much when I list them, but we'll look at them in detail as we go. So the first is we have to have baryon number violation. Okay? And I'll explain exactly what I mean by baryon number violation in just a moment. The second condition is that we have to have both C and CP violation. And the third condition is that we actually have to have a departure from thermal equilibrium. So we have to have something which is generating a non-equilibrium state. Okay? So let's start with the first of these and see if we can understand what is meant by baryon number violation. First of all, to define what I mean by baryon number, we're just going to make a definition. So baryon number is defined as follows. For each baryon, so that is for each proton, for each neutron, for each, any higher mass baryon, if you like. For each baryon, you give it a +1, and for each anti-baryon, you give it a -1. And then for a system, a collection of baryons and antibaryons, the net baryon number is additive. Okay? Now you might say, of course you would add those numbers together. Well, that's not always true. Sometimes when we assign numbers and then we want to assign a number to an entire system, it's multiplicative. Okay, we'll actually see an example of that in a few minutes. But for baryon number, it's literally just additive. Okay? For example, in a symmetric universe, that's the way we expect the universe was born, the net baryon number is 0, exactly. Okay? In our current universe, the net baryon number is
10 to the 80.
10 to the 80. Good. Okay? So the idea here is how do we actually get the net baryon number to change from 0 to 10 to the 80? 10 to the 80. Okay? Now, baryon number violation is basically undoing the idea of baryon number conservation. Okay, so this is something that we explain to Physics 1 students, perhaps not always successfully. But when we say that something is conserved, do we mean that it's constant? No. If we say that something's conserved, that just means that we can explain the change in the quantity via the flux out of or in through a surface bounding it. Okay, so my favorite example is the number of students in this room is a conserved quantity, because for the number of students to change, I could explain that by people leaving the room or more people coming into the room.
It's not wholly correct.
It's not wholly correct because you can reproduce. And this weekend, I don't know. I have to increase the grading spreadsheet by 1 or 2. Anyway, but yes, modulo reproduction. The number of students in this room is a conserved quantity. Okay. Now, what's important though is that if you apply a conservation principle or a conserved quantity to a system that is the entire universe, there is nowhere for things to go or for things to come from. So applying considering a conserved quantity for a system that comprises the entire universe implies that that quantity is constant. Okay? But if baryon number was conserved and the universe started with a baryon number of 0, it would remain 0. So we have to violate the conservation of baryon number in order to generate a net baryon number. Okay? So here's the tricky part. If we take the standard model Lagrangian, which I showed you at the beginning of the semester, we've slowly pieced together various parts of it, and you start studying processes using the standard model Lagrangian and the Feynman calculus as you apply it to perturbative processes, what you'll discover is that when you start drawing diagrams for various processes in the standard model, you're always going to have the same baryon number that's coming in as you have coming out. You literally can't draw a diagram using the Feynman vertices. Now, we haven't written down the vertices for the strong and the weak interactions, but trust me, when you write them down and include them in addition to QED, you will not be able to construct a diagram for which the initial baryon number is different from the final baryon number. Okay? So what this means is that in any process described by the Feynman calculus or the Feynman rules in the standard model, there is no way to explain this. It's simply not there. Okay? But the good news is that this is not the only thing that happens in the standard model. The Feynman rules apply to particle-like excitations in their behavior. It's a perturbative treatment, right? We take the Lagrangian, we expand fields in small fluctuations around some solution, and then the Feynman rules are actually applied to the fluctuations. Okay? So for example, when we want to apply the Feynman rules, if we think of some potential for, say, some matter field, some spinor field, and this potential has an interesting structure, we can use the Feynman calculus to sort of describe fluctuations around different classical minima. So Feynman diagrams might describe how these fluctuations are behaving, or they might describe how these fluctuations are behaving, depending on what background field configuration psi naught we choose. Okay? But here's the key. These diagrams are never, ever going to be able to describe something we know can happen, which is the tunneling from here to here. Because tunneling is non-perturbative. Okay? A small fluctuation is sort of by definition stuck in its valley. If you fluctuate and go over the hump down here, that's not small. Okay? Now, do we have non-perturbative type things in the standard model?
The breaking of the Higgs mechanism.
The Higgs mechanism is a non-perturbative phenomenon. There is a Higgs particle, but the actual breaking of the symmetry that gives mass to all the fields in the standard model is something like this, where you move from one valley to another valley. Or actually, in that case, you move from a local maximum to a valley. But nonetheless, that change is non-perturbative. So we already know there's non-perturbative physics in the standard model. It turns out the Higgs part itself is not going to be able to create baryons, but maybe there are other non-perturbative things that can happen. And it turns out that there is a non-perturbative process in the standard model which will suit the bill. In the electroweak sector, so first of all, if you just try and use electromagnetism, it ain't going to happen. If you just try and use the strong interactions, it ain't going to happen. But if you look at the weak force, and since we're in the early universe, we should really be working with the electroweak unified force. But if we look at the weak force, then we discover that there is a series of minima which are degenerate in energy. So you could think of this as some potential for some matter fields. And what's important about the different possible minima is that they differ in their total baryon number. So if this has some total baryon number, just call it B total, then this would have a B total, which is different. And it turns out that for the specific standard model Lagrangian process, the difference is by a factor, or a set of 3 baryons. Okay? And then over here, this might be -3. And this continues. Okay? So now what we can imagine are processes which basically move us from one of these vacuum to another. And if we move from this vacuum to this vacuum, we've gained 3 baryons in the universe. Our baryon number has increased by 3. If we move from here to here, we've increased it by another 3. Clearly, we got to do a lot of these to get 10 to the 80, but we got the history of the universe to get that done. Kowalski.
The x-axis there, is it like actual, or is it?
It's psi, kind of. Yeah, the idea is that these are different configurations of the psi field.
Okay, all right.
So this is technically, this axis is the space of psi vacua. You want to go home and tell your friends that you
Yeah,
learned
I will.
something in particle physics. I heard about the psi vacuum today. Yes?
Why is moving to the right favored? Because if you can move equally in each direction.
That's an incredibly important observation. You can move either way, okay? And that's an issue that we're going to have to address. Okay, so the first observation is that within the standard model, there is a mechanism to change baryon number at all. Okay? Because remember, to get from 0 to 10 to the 80, the baryon number has to change. And using perturbative processes, it's stuck. If it started at 0, it's forever 0. At least with this non-perturbative process, we can change it. But the issue, as he pointed out, is that the arrows go both ways. So I can imagine a process which increases the baryon number, but this same mechanism allows me to decrease the baryon number. Okay? And you can think of it as increasing baryon number is creating baryons, and decreasing the baryon number is increasing the number of antibaryons. Okay? So what we need to do is we need to find a way to sort of force this to go in one direction only. Okay? It's to only increase the baryon number. Specifically, if we start at 0, we want to enter 10 to the 80. Okay? So that's where the second condition becomes important. We need to have C and CP violation. So let's start with C violation. And by the way, if you end up interested enough to study this, there's a couple of words that get attached to this. First of all, if you actually achieve this through tunneling, so the energies are low enough that fluctuations can't actually get over the hill, you can get there quantum mechanically by tunneling. In that situation, this process would be described by an instanton. And you can calculate a transition amplitude based on instanton methods. If, however, things were hot enough that fluctuations could occasionally actually jump over the barrier, then we're dealing with what's often called the Staleron version of the process. Okay? And just to be honest, in this process, there actually is something that is conserved, even though baryon number is changing, and that is the B minus L, the baryon minus lepton number. So if we defined and assigned a lepton number associated with the number of leptons, then we would find that in these processes, this number remained constant. But that's a technicality we don't need to worry about. I just want to be honest with you. Because I know you're all keenly sober and on top of the many details, technical features.
So experimentally, a lot of people are looking for a lepton number violation rather than baryon number violation. Is that eventually to track back to this question?
I'm not 100% sure about the motivations, to be completely honest with you. It's not only for this. I don't actually know off the top of my head what the consequence.
Well, I'm just trying to poke a hole in the standard model since we know it's not entirely correct.
Right, yeah.
It's if you make baryons, you destroy leptons.
It's if you create 3 baryons, you also create 3 anti-leptons.
Yeah.
That would preserve B minus L.
But not L.
I'm not 100% sure. I'd have to think about it more or go look up something. But lepton number violation on its own, I think, has other consequences in the standard model beyond just the baryon asymmetry. It obviously plays a role if this is the process by which we would be getting the baryon asymmetry. And I should say, so to be completely honest, this is a proposal, this is part of the standard model. It's not clear if this is the exact mechanism, if it's the only possible way to do it. Again, you're dealing with, these are non-perturbative calculations. You don't have Feynman rules to evaluate amplitudes with. So you're doing non-perturbative calculations in a cosmological context, so there's a lot of moving parts. So it's not 100% completely accepted that this is the explanation. This is just a proof of principle that somewhere in the standard model there's B violation. Okay? All right, so what does C and CP violation have to do with the story? Well, as was pointed out, if we imagine that early in the universe there was a process that was creating baryon number, then that would actually be competing with a process which was decreasing the baryon number, because if you can move to the right, you can move to the left. Okay? And so in the end, if these two things are happening at the same rate, and you started with a baryon number, a net baryon number of 0, you're not going to really deviate from that. You might occasionally fluctuate a little bit above or below, but you sure as hell aren't going to fluctuate to 10 to the 80. Okay? Unless you're really, 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 lucky. Okay, so how do we actually fix this problem? And the first thing we're going to talk about is charge conjugation. So, charge conjugation C has a technical definition, but its sort of simple idea of charge conjugation is that C replaces particles with their corresponding antiparticle. Okay? Now, it does change the electric charge, hence sort of the name charge conjugation, because we know if we go from an electron to a positron, we go from a negative electric charge to a positive electric charge. But C conjugation also does something non-trivial to neutrinos, which have no electric charge. So it has an effect beyond just what we think of as electric charge. One way of defining it is that it reverses the value of all internal quantum numbers for a particle. Okay? But at any rate, this is the effect of charge conjugation. And what we could imagine is asking if charge conjugation is a good symmetry of the standard model. And we know that it's a good symmetry of the standard model for some processes. So for example, if I considered electron-electron scattering into, say, muon-muon, and let's be creative, and that's absolutely wrong. Actually, yeah, we'll do that. Okay, so two electrons scatter and then 2 muons come out. You can connect that with some funky Feynman diagram. And then you can calculate the scattering amplitude associated with that process to maybe first order. Then you could charge conjugate the process. And if you charge conjugate it, that just means replace everything by its corresponding antiparticle. And then you would calculate the scattering amplitude for that process. And what you would discover is that these two are actually the same. Okay? Now, you don't have to take my word for it. In fact, you're not, because you're going to do this as part of your homework. That's why you're glad you're visiting this class. But you can actually almost see, because you've done enough of these calculations, you can almost sense that when you do the Feynman rules for this process, it's really not going to look any different at the end of the day.
V's and U's.
Okay? In particular, all the masses involved are the same. So this is an example of a process where charge conjugation is a good symmetry. But we need charge conjugation to not be a good symmetry. So we could ask, is there processes in the standard model where it's not good? And it turns out that there are. So in particular, if I consider the decay of a pi plus, so this is a little meson. It's on your little list of particles. It's actually one of the lightest mesons. The pi plus typically decays into a anti-muon plus a muon neutrino. Okay? And now you have to put on your physics hat for just a second because I'm going to say something technical. Okay. And that means yes, Ashley, there will be a question. If the pion starts at rest, its momentum is 0. What can you tell me about how these two things have to emerge from this decay?
Their combined momentum has to be 0.
They're what?
Together, their momentum has to be 0.
So they have to emerge back to back.
Yeah.
Okay? So one of them has to move to the left, and the other one has to move to the right. Okay? Now, Ashley, because you're on a roll, you want to take another sip?
Yeah.
Now I'm going to tell you the following. The pi plus is a spin 0 particle.
So pi minus is spin 0.
So the pi plus is a spin 0 particle. Okay?
Yes.
So P is 0, L is 0. What can you tell me about the relative spins of the muon or the anti-muon and the muon neutrino.
They also have to be opposite.
Yes, the spins of these are both spin-and-a-half particles. The spins have to be anti-aligned. Because if you want to add two half-integer spins and get 0, you have to have them anti-aligned. So their spins have to be anti-aligned. Okay? And now we have momentum vectors and spin vectors, which is begging for us to talk about bag of hands. Bag of hands. I know. Bag of hands. Handedness. Bag of severed hands. So we're lots of severing going on today. Okay, so I actually drew this backwards. Let me fix it. So these are actually going to point inward. They're still adding to 0, okay? But with this identification of momentum and spin direction, this is what we call a left-handed particle. I'm just going to call that left H. And this also is left-handed. Okay, remember, to get the handedness, you basically use the right-hand rule. Okay, so you can kind of think about the direction of the spin as coming from the curling of your fingers of your right hand, all right, and then whether that aligns with the momentum direction or not. Okay, if it aligns, if your thumb also points in the direction of the momentum, in addition to the spin, then it's a right-handed particle. In this case, it doesn't, so it's left-handed. All right? Okay, everybody on board with that story? Okay, we see this a lot. And you can calculate the amplitude for this, and you'll get some m, and that m is not 0. But now, let's consider what this story would look like if we charge conjugated it. Okay? If we charge conjugated it, we would have a pi minus decaying into a mu minus and an anti-muon neutrino. Everything else stays the same, so the total momentum of the pion is 0. It starts at rest. It spins 0, so the angular momentum is 0. So these things would move away back to back, and they would still have the same spins. Okay? There's no reason why changing the particles and antiparticles changes any of this space-time stuff. Okay? And then you can calculate m for this process, and you find that it's 0.
Is that bad?
So the answer to Emily's question, is that bad, is no, that's not bad, that's good, that's exactly what we want. Thumbs up from Emily. Good to go. Okay? Why? So why is this useful to us? Well, think about it. If I come up here, there's a certain sense in which this process is the charge conjugation of this process. Okay? In particular, if I started out with, say, some B total incoming state that's 0, the initial stage of the universe, and then through some Spaleron process, it created a B total. Well, I'll just say B initial is, or B is 0. I'm not going to write total everywhere. I increase this to +3 by adding 3 baryons. Okay, then charge conjugating is not going to change what's coming in, because if your B total is 0, you're always just going to be switching baryons and antibaryons. B total is still going to be 0. But now you would be, instead of adding 3 baryons, adding 3 antibaryons. Okay? What we would like is for one of these to occur with a different probability than the other. And we already know that in the standard model, there are processes for which one version and the charge conjugated version happen with different frequencies. Okay? Now the good news is that charge conjugation only happens in the weak interactions. It doesn't happen in the electromagnetic interaction. It doesn't happen in the strong interactions. It only happens in the weak interactions. But these Spaleron processes are in the electroweak part of the standard model. Okay? So it is entirely plausible that the charge conjugation violation is going to be the thing that makes these arrows go one way. Okay? So that's good, But unfortunately, there's a pitfall. And that is that there's another version of this process we have to consider. Okay? And that is what happens if we don't just charge conjugate, but we also CP conjugate it. So P, and by the way, because you all might not be like totally at your best and on top of your game in this moment, and I'm using words that you kind of know, when I talk about, I didn't hear that and I don't want you to repeat it. When I talk about charge conjugation violation, I'm not talking about non-conservation of electric charge. Okay? Electric charge is conserved. That's not going to change. This is charge conjugation of a process and whether the charge conjugated version happens at the same rate. Electric charge is conserved, and we're not trying to mess with that. Okay? It's an unfortunate double use of the word charge here. Okay, so CP is a combination of charge conjugation and a parity transformation. Now, a parity transformation, and for those of you who remember anything that we talked about early in the semester when we talked about rotations, and we talked about O3 versus SO3 and what we were getting rid of, the transformation we were getting rid of was parity. And the simplest way to think about parity is that if you put a mirror up and you're standing there and you hold out your hand and it's like that, then your mirror image looks like this. And there is, and remember, your face is this way, both there and in the reflection. There is simply no way to take you here and rotate you to here. Does everybody understand that? Or in 3D. Like literally, I can't take this and rotate it. I can flip you over, but then you'd be facing the other way. Okay? So this transformation is not a rotation. It's what we call a parity transformation. And in this case, it's just a reflection around one axis. We could call it the x-axis. Okay? Now, we learned some important things about parity. For example, if you try and do it in two directions at once, that doesn't work because that's actually a rotation. You have to invert an odd number of axes in order to have a true parity transformation. So in 3 dimensions, we can either invert all 3 spatial axes or we can just do one. Typically, we just do one. It makes the pictures easier to draw. So really quickly, we have to know what parity does to this story. And what parity does in general is if we have, say, a momentum in some direction, and then we have a spin associated with the particle that's moving in this direction, and I'm just going to have the spin going this way. So for the moment, we would think of that as a spin in this direction. If I parity transform this story, okay, then in principle what happens is the momentum changes direction, but the spin does not. The spin is still to the right. Okay? Now that might seem weird to you, but there's lots of words to attach to this. Momentum is a true vector, and true vectors pick up a minus sign under a parity transformation. Spin is a pseudo-vector. Pseudo-vectors do not pick up a minus sign under a transformation. Another way to think about it is any angular momentum you can kind of think of as a cross product of 2 true vectors. But if you have 2 true vectors and they both pick up a minus sign, their product doesn't. Okay? So there's many different ways to approach this, but the point is if I do a parity transformation, momentum changes direction, the spin does not. So now if I do the CP conjugated version of this, I have P minus with 0 momentum, 0 angular momentum. It's going to become, and it doesn't really matter which direction I do this, but if I say it becomes a muon minus moving to the right, and with spin to the right, plus, oh my gosh, my picture's getting crazy, an anti-muon neutrino now moving to the left, but with spin moving to the left. Then, when I calculate the amplitude for this process, I find that m prime is exactly the m over here. Okay? Now, why is this a problem? Well, it's a problem because in trying to apply C to make these things different, we didn't really talk that much about handedness. And so it turns out that if this process, for example, created right-handed baryons, then this process would happen with the same frequency. The only difference is it would create left-handed antibaryons. But when you're calculating baryon number, you don't distinguish right-handed from left-handed. You just add them up.
left-handed anti-baryons can still cancel right-handed baryons?
Yes. Okay. In fact, for massive particles, left-handed and right-handed is really not that important of a distinction because you could change it with a Lorentz boost. Okay, so in order to actually get this to work, we have to not just violate C, but we have to violate CP. We're violating everything today. I feel violated. Okay, so does everybody, yeah, Oreo.
Does the parity transform act similarly on photons? Have an issue because you want to be able to change the density? Is that?
Sorry, say it again. Yeah, parity will reverse the helicity of a photon.
Okay.
Yeah. Of course, charge conjugation doesn't do anything to a photon because it's its own antiparticle.
Yeah.
Okay. Okay, so the good news is that CP violation also happens in the standard model. Okay, now in this example, you don't see CP violation. You see this process and then you see this process and they have the same amplitudes. So that might lead you to think, oh, CP violation is not there. But it actually turns out to be in the standard model, and okay, so we will study, when we look at the weak interactions, we're going to look at this thing called the Kabibo-Kobayashi-Moscawa mixing matrix, and it's in the CKM matrix. There's a poster on the SPS office right around the corner that talks about this BTW. It's right there. But anyway, one of the features of the Kabibo-Kobayashi-Moscawa mixing matrix is that it is actually the source of CP violation. It's one source of CP violation in the standard model. So the standard model does have some CP violation built in. It's questionable whether that source of CP violation is enough to explain the baryon asymmetry, but at least as a matter of principle, we know there's CP violation in the standard model. That's different from charge conjugation. This is maximal. Right? You either have something non-zero or zero, okay? But the CP violation is actually a very small feature of the standard model. And it took a long time to get discovered. But anyway, okay. So we know why we need baryon number non-conservation. We know why we need C and CP violation. What about this equilibrium part of the story? And this is, yet again, one of those things where we seem to have a no-go unless we think carefully. All right, so right now, when I've been talking about the rate of this versus the rate of this is really just thinking about, okay, there's sort of one reaction going on. I have like a zero baryon number state, and is it going to increase by 3 baryons or decrease by 3 baryon number, okay? However, the early universe is this hot mess, right? You got a soup of highly energetic particles. You're creating very massive particles. There's stuff flying around with lots of energy, lots of angular momentum. You've got a lot of interactions going on. This is not a single isolated interaction that is the entire universe, okay? It's a macroscopic system of things going on. And one of the lessons that we learn from as early as chemistry, I know you remember a lot of your chemistry class, is that in a large system, in thermal equilibrium, we have to expect that the rate of a reaction in one direction equals the rate of the reaction in the opposite direction. Because remember, this reaction itself can be run in reverse. So we can literally take B plus 3 and use the exact same process to create 0. All right? And what happens is if you start with a symmetric universe with no net baryon number, and then you start letting it evolve, this process with CP violation and baryon number violation, it might start generating baryons. But once you get enough baryons present, they're going to be saying, hey, we want to do something. Why don't we get together and run this backwards? And so eventually you're going to equilibrate between the two sides. So in thermal equilibrium, and this is the same kind of situation that you encounter when you try to get population inversion to get a laser to laze. Okay, so you've got to somehow get away from an equilibrium scenario. Otherwise, just the equality of reaction rates in either direction is always going to wash out the difference. Okay, so we can ask, well, are things in thermodynamic equilibrium? And the answer, fortunately, is we know that they're not. And it goes back to this Phaleron process. What's interesting about this Phaleron process is that this is changing the vacuum of our quantum field theory, but another way or another language we can talk about that is that it's just a phase transition. The vacuum is sort of the underlying configuration on which things are fluctuating. If you change the vacuum, you can kind of think of it as a phase transition. Okay, it's some very large change in the underlying structure. And it turns out that this particular phase transition is first order. And one of the interesting aspects of first order phase transitions is that they can proceed via bubble nucleation. Okay? So what do I mean by that? Well, first of all, if this was our universe, and we got a hot mess of stuff going on, if the process of moving from here to here happens sort of smoothly everywhere at once, okay, then we could imagine moving from here to here and remaining in thermal equilibrium. And in that case, these differences would wash out. However, for first order phase transitions, you can have the formation of bubbles where in the bubble you have the new vacuum, outside of the bubble you have the old vacuum, and then the phase transition actually occurs by these things nucleating and growing and either taking over or colliding with each other, and things get interesting. And you should be thinking about boiling in this context, right? So the new phase is water vapor, the old phase is liquid water, and if you wait long enough, the water vapor wins. But it proceeds through this bubble nucleation. Okay, and there's lots of other phase transitions in physics that can happen with bubble nucleation. And by the way, the reason why bubble nucleation tends to occur is because it's easier to get a localized fluctuation that's big enough to do something than to get the whole system to go whoa and have the change in energy to move from one vacuum to another. I'm not going to do it again. It's so awesome. Never try and repeat awesomeness. Awesomeness is singular. No. Okay, so the good thing is that when you have these bubbles that are forming, you have a very big difference between the region outside and the region inside the bubble. It's definitely not in equilibrium. Okay? So the bubble walls themselves of the Phaleron process, which we use to get the baryon number violation, provides us with exactly the non-equilibrium condition that we need. Okay? So all I'm trying to argue to you is not that this is exactly how it happens, but that all three of these things are necessary, and there is at least some evidence that all three of them exist in some form or another in the standard model. Okay? And this is still an ongoing question. The details have not been completely hammered out or agreed upon. And so, if this is a question that you find really interesting, Joe Bales, then you should at some point think about doing some research on it. Okay? All right. Any questions about why you matter?
Why isn't there an anti-process to each of these that cancels out each of the effects of each of the processes?
What?
Why is there not a CP violation in the other direction, or a non-equilibrium in the other direction? Like, is there only CP violation that helps that B plus?
CP violation is not something that goes in a direction. You take two things in one direction, and they're related by CP.
Yeah.
And then you just ask, they're related by CP, do we have the same rate for both of them? If we do, then CP is a good symmetry. If they're not, then CP is a bad symmetry.
But the CP or C charge conjugation that you presented had a mechanism for increasing the baryons, or no?
The C conjugated process that I drew,
Yeah.
it did change the sign of what came out, but then I said that process did not happen. It didn't exist. We don't see it. So the fact that we see the original version and not the C conjugated version means that this one can happen and this one can't.
Yeah.
Okay, I don't want to stay on this too long because I do want to get to what is hiding in the closet. Yes, all right.
Does this relate to, I think they're looking at like electric dipoles to see if those relate to the difference in baryon numbers? Is that related?
I am not completely fluid in the current research into this problem. Okay, so I mean, I would be happy to look into those questions for you. But yeah, you can always come and talk to me after class. Okay, so you did your time. Now we're gonna have fun. Okay. So I appreciate you bearing with me through that. That's a legitimate discussion because you are gonna have a homework assignment out of it. I know. But now let's have some fun and address some of these other questions. Okay, so first of all right. So in mathematics, we often, if you're not familiar with math, no. So seriously, if you're not familiar with the way that math works, the way that math works is you write down a set of assumptions, or sometimes called axioms, and then you just explore the logical consequences of those axioms. Okay, that's math, and you get to start with any axioms you want, and then explore them. Okay, and sometimes you turn up something useful, and sometimes you don't. Okay, when you do this, when you define certain structures in math, it's typically the case that you find that based on your definitions, you can sort of generalize the structure to arbitrarily high examples. So just to give you an example, in group theory, and so the people in my class know a lot about group theory, people that are not in the class might not know so much, but in group theory, we, for example, can talk about matrix groups, and in particular, a very important set of matrix groups are the special orthogonal matrices in n dimensions, and these have various nice properties. They're Lie groups. You can talk about their generators and so forth and so on. They have different representations. But the thing is that the words we use to define this in no way, shape, or form restrict how big n can be. N can be any positive integer. Okay? So we've defined a mathematical structure, but there's no reason to think that, like you get to SO12 and it ends. Like it would be weird if I said SO12 is as big as you can get. Okay? Actually, though, let me give you an example of where SO12 is the biggest you can get. Okay? So, for example, consider if I asked, how big are the S n-spheres that can be embedded in 13 dimensions? Okay? So I'm thinking of a 13-dimensional space, and the question is, how many dimensions of spheres can I fit in there, or can I embed in there? So first of all, we know we can put a 0 sphere in there. That's just a point. And we know we can put a 1 sphere in there. You can take 13-dimensional space and draw a circle in it. Okay? And you can put a 2 sphere, and you can do this all the way up to an S12. Okay?
Sure.
It would be hard to embed a 13-dimensional sphere in 13-dimensional space. If for one of the reason, if I'm thinking of embedding it in 13-dimensional flat space, because the 13-dimensional sphere is curved. So we know how this works. For example, in 3 dimensions, the biggest sphere we can put in is the S2. That's the surface of a 3 ball. The biggest thing in 3 dimensions we can put in is an S2. Okay? But if I then think about the isometries of these spheres, the transformations I can do which leave them unchanged, this of course is just the identity. There's nothing you can really do. This is SO2. If I have a circle, I can rotate it in a plane. This is SO3. If I draw the 2 sphere, I can do 3-dimensional rotations and it looks the same. And then it's obvious that if I carry this up, this becomes SO12. So here is an example of a mathematical structure, in this case groups. Oh, sorry.
one in this case, but not.
Yeah.
Oh, no, sorry, SO13. Yeah. Why did I pick? No, yeah. Sorry. No, 13 and up to 12. Yeah, so SO13. I don't know why I did that. Okay. All right, so the point is, here's a mathematical definition, and there's kind of a top limit. It doesn't make sense to ask about a 13 sphere in 13 dimensions, and therefore SO14 would not really be relevant. Okay? However, we know why this is happening. It's because here's a number.
Yeah.
Our whole question is predicated on me introducing a number, and it's intimately tied to this maximal number. So if your definitions already have a special number, it's probably not surprising that a special number appears in the possibilities.
Agreed.
Okay? Where it gets interesting is when your definition has no special number, and yet you find some kind of limit on what you can do. Okay? Here we go. All right, so let me give you an example of how this happens in math. So let's first of all go back to an example, and I'm going to talk about group theory because that's a mathematical topic which we've used in this class and you're all relatively comfortable. Ashley in particular is super comfortable.
Oh, yeah.
So let's actually talk about a group that you have explored before, and I'm just going to call it the triangle group. I know. Okay? So the triangle group in 3 dimensions has a set of transformations we can do. And the idea here is that I only do transformations where the corners end up where corners were before. Okay? And this is an equilateral triangle, and I'm just labeling the vertices to keep track of what's going on. So I know I can rotate it by 120 degrees, class, not 60. And I can do that again and get a triangle with this labeling of the vertices. So technically this is an R240. Okay? Now, I'm going to include another set of transformations. See you, Jeff. I'll do another set of transformations, and that is I'll imagine what happens if I take this and I rotate it in 3 dimensions about an axis through the B vertex. So in this case, all this does is switches A and C, but it leaves B fixed. And then I'm going to do an analogous thing with the other vertices, and this one I'll do through the C. So now this becomes B, this becomes A. And then if I do it through the A, this becomes A, this becomes B, and this becomes C. And so for this set of transformations, we have a group. And the elements of that group are the identity, Ashley, and what else?
Let's go.
R120.
R120.
Yeah. R240.
Woo!
Hi.
And another 3.
Yeah, so let's just call these FB, FC, and FA. Okay?
You got it, girl.
Get it, girl.
Good job, Ashley. You made me proud. Okay, I'm going somewhere with this. Okay, so first of all, let me introduce just a word that we'll encounter later on. If I have a finite group, the order of the group is basically the number of elements. So the order of the triangle group is 6. Okay, there are 6 elements in this group. Okay. Now, based on that triangle group, we can write down a couple of subgroups, right? So some subgroups of the triangle group are I, R120, and R240. Ashley, your card happened to be on top.
Yeah. Crazy.
Can you tell me another subgroup of the triangle group?
Well, you have to have I.
Yes, exactly. Nice.
And then all 3 of the F's.
Actually, you could just do one of them.
1 of the F's.
Because the nice thing about the F's is they are their own inverses. If I do an FB and then I do it again, I get back to what I started with. Okay? So we have a bunch of subgroups. of the triangle group. All right? So it turns out to be exceptionally useful to define and identify normal subgroups. That was a joke, but thanks for getting it. Jerk holes. Exceptional, normal. Screw you guys. I'm going home. Go to hell. Okay, no, I'm just kidding. Okay, so here we go. So let me define. Shh, I'm getting somewhere. Trust me. So I'm going to define a normal subgroup for you. So here we go. A normal subgroup H of G. So if I have some group G, and I want to define a normal subgroup H of it, is such that GHG inverse is H for any G on G. Okay? Now, let me explain this, and I'm going to show you an example of what I mean. First of all, this does not mean that GHG inverse equals H for any H on H and G on G. Okay, what it means is if I take the set of all elements of the subgroup and I do this operation on them, I get back the whole set, but it might shuffle them around. So it's not a one-to-one mapping between an element of H to the same element of H. Okay? So with that in mind, let me identify a normal subgroup of the triangle group. Okay? So it turns out that one of these small subgroups is normal, and let's prove that. So what I want to do is take the two elements of this and ask what happens when I do this. It's called a conjugation by G. And just to be concrete, let's pick an element G to be a rotation by 120 degrees. It'll end up working out for any other G, but I just want to show you the details. I really... Okay, so what happens if I do this to the identity? If I take G identity G inverse, with G being a rotation by 120 degrees? Ashley! It's the identity, because everything commutes with the identity. So this literally just becomes G inverse, which is the identity. I feel like I've been having some of that. Okay, now let's do this one. A little bit trickier, but let's watch. Okay, so I do R120, FB, R240. Notice G inverse is R240. Right? Rotating by minus 120 degrees is really the same as rotating by 240. So let's actually act on A, B, C with this. So if I do the R240, I'm going to get this. R240 flips this thing around to A, B, C. Everybody agree? I'm trying to keep this simple so you can follow it. Okay, so then R120, we're going to do the FB flip, so we're going to flip around the B axis, and so that's going to give us this. And then if we do an R120 on that, that's just going to give us a 120 degree rotated version of this, which is ACB. Okay? But this is exactly what I get if I just apply FB to what I started with. You're killing me. You're like, okay, before I proceed, I know the people in the back of the room are getting this.
I get
Do
it.
you? Okay, I got faith in you. Faith in you. Does everyone in the back of the room follow this? Okay, good. Just as long as if there's three of you that are following. Okay, Caroline's on top of this too. Okay, so I have just defined a normal subgroup for you. Okay, now I'm going to define something that's really complicated. A simple group. That was jokes. You guys are really on the jokes today. Screw you guys. I'm going home. Okay, so the simple groups. Simple groups have only have only 2 normal subgroups. This is about to be the end of this technical part. So a group is simple if it only contains 2 normal subgroups. And those normal subgroups are, so G is simple if the only normal subgroups are the identity
And something else.
and G itself.
Oh.
It turns out if you take the entire group as a subgroup, it's normal. I know it's weird. Okay? You've got to be kidding me. I'm going to answer the question that you asked.
The rotating black holes.
No. But you go on, you watch the video, you go on. No, I would hate for you to stay and learn something amazing. Okay. Hey, do you guys notice a structure? Do you guys notice a structure like this anywhere else in mathematics?
Yeah, prime.
Yeah, prime factorization. Okay. So there's a certain sense in which simple groups are kind of like prime groups. Okay? All right, so now here was an interesting question that mathematicians thought to explore. They asked themselves, can we classify all finite, now this just means we're going to consider discrete groups. We're not going to talk about continuous groups because a lot of this doesn't even apply. So we're just going to look at discrete groups. Can we classify all of the finite simple groups? That is there just an infinite number of possibilities, or is there some kind of at least classification structure that we can find and describe every possible finite simple group? And it turned out the answer was yes, but the answer itself for what those classifications are is very, very interesting. So first of all, let me give you an example of a finite simple group. So one finite simple group is the group ZM. And the group ZM is generated, it's not a continuous group, so these aren't generators like in a Lie group, but still this is an element from which you can build everything else. This is generated by G such that G to the M equals the identity. Okay? So what I have in mind is if I wrote down the elements of this group, I would have the identity, I would have G, I would have G squared, I would have G cubed, up to Gm minus 1, and that's the set of elements in the group. Okay? I wouldn't include Gm because Gm is the same as the identity. All right? So this is generally called the cyclic group. But here's the thing. Clearly, I can choose M to be any number I want. Okay, say it again? No, it's not a trap. This definition of this group has a parameter, M, that I am free to choose to have any value I want. Okay? So this is a family of groups. The different members of the family are just different choices of M.
Sure.
Okay? Yes, Will.
Do you lack a coupling in that group? Because I feel like when you're taking your exponents of G to generate the group.
No. This is not a continuous Lie group. That's why I say generators in parentheses. This is a discrete group.
Oh, okay.
This is a discrete. There are only M elements in the group. A Lie group with generators and the exponential map, that's a continuous group. It's got an infinite number of elements. This is simpler than that. Okay? So I want you to understand what I mean by a family of groups. If I say the cyclic group, well, that could be Zm for any M. And there's no reason that M can't be as big as you want. Okay? Now, what's interesting is that there were a lot of mathematicians that studied this problem, and what they discovered was that there were 18 families. 18 families of finite simple groups. Where what I mean is each family has got some parameter. In some cases it's 2 parameters, and you can keep adjusting the values of those to create different groups, but they're all defined by basically the same statement. Like all of the cyclic groups are defined by this.
Yeah.
And then the only difference between them is changing M. Now, I'm not going to write down what these families are, but in general, there are 18 of them, okay?
It's a very arbitrary number.
Yeah.
Well, no. Okay, so yeah, that's an interesting thing. There are 18 of them. But what is perhaps not as interesting is that in all of them, the parameters can go arbitrarily high. Okay? In some cases, the parameters can't go arbitrarily low, but they can go arbitrarily high. However, that's not all of the finite simple groups. It turns out that there are, how many are there? I think it's another 16. Now I don't have the number, but I can't remember. But anyway, but there's another set called the sporadic groups. Okay, so what do I mean by sporadic groups? So these are finite simple groups, but they are not members of any of these families. In particular, you don't get these groups by picking one of these families and setting the parameter to a certain value. Okay? So they're different than these, but more importantly, each of these sporadic groups does not have a parameter. It simply exists with one value of some number.
Okay.
It's not defined using a number,
But it has a
but it has a special number that is associated with it that emerges for sometimes not well understood reasons. Okay? Now, these sporadic groups are very hard to study. The smallest of these sporadic groups, if I want to give it a name, is it's called M11. And it is the, just to let you know exactly what it is, it's the Matthew Sharp 4 transitive group acting on 11 symbols. Okay? So for anybody who wants to just go home and tell your parents about a sporadic group, just to tell them about the simplest one, you can just talk about the Matthew Sharp 4 transitive group acting on 11 symbols. Okay? Now you might say, well, how big is this group? How many elements does it have? What is its order? Well, the order of this Matthew group, and this is the smallest of the sporadic groups, the order of this is a lowly 7,920. So if you were really going to write this out for the Matthew group, you'd write down 7,920 elements. So that's a pretty weird number.
Yeah.
That's a
Really strange number, okay? But of course, you should go big or you should go home.
True.
So if you're going to talk about this set of sporadic groups, what do you really want to know?
the biggest.
The biggest. And it turns out that of the sporadic groups, there is a largest one called the monster group. Affectionately called M. Not to be confused with Minkowski space. How big is the monster group? You're going to need some more paper. The monster group, and you can actually work out the number exactly, but I'm not going to write it, is approximately of order 8 times 10 to the 54. So the number of elements in the monster group is of order 10 to the 54. Now I want you to think about the ways that mathematicians have to study these. They clearly don't write down like 10 to the 54 things, right? So there are ways of teasing out the properties of these groups, but they're by no means simple to just like write down. Like you can't do it, okay? Now, you might say, well, you know, this is the biggest, but how big is the next biggest? Is this like really an outlier? And it turns out that the next biggest, which is called the baby monster group, has order 10 to the 33 elements. So the baby monster would have been big except for the monster, and the monster is way bigger than the baby monster. Okay? Now, okay, so in mathematics, remember, we're defining these structures without putting in a number like 8 times 10 to the 54. Okay, in a lot of cases, we're not even putting in a number. We're kind of putting in concepts, and then these numbers are popping out. So now what I want to do is I want to make an interesting observation. Well, first of all, when mathematicians were looking at this monster group, they wanted to make sense of it. They were like, I really want to know why this thing exists. It would be really interesting. Okay? So when they couldn't figure out why it exists, they couldn't really get, an understanding, they did what you would all do when you want to give up. You
Give up.
Exactly. Ashley had it right. You drink. And so there is a drinking part to this story. And the drinking part to this story goes as follows. This is shit. This is. Hold on, I gotta find.
What was that, Tarleton?
Oh my God, no!
Alex, you gotta speed it up.
Okay. I
How is the longer this lecture takes, the longer I can wait to work on the rest of the Please keep going.
I kind of think it would be hilarious. Did a page of my notes in the room?
We ate it.
I hope to God you didn't. Okay, I am never going to remember these numbers, but fear not. Hey, Ashley, go to the bathroom. Come back. If anybody leaves and doesn't come back, I'm going to start punching babies.
I will punch you back.
Baby monster. I'm sorry.
Everyone got like.
Okay. And I got it, guys. Hold on, I got it. We're good. Oh, no. Don't do that. Don't do that, computer. Okay, here we go. All right. Wolfgang, I'm going to give you a bad senior design grade. Okay. All right.
Welcome back, bud.
Damn right. Okay, here we go. Okay, so here we go. So an important observation was made about the monster group. All right? An important observation was made, and that is that if you want to create representations of the monster group, I don't know what the hell's happening on my computer. Okay, if you want to create representations of the monster group, then it turns out that, so remember, representations are the objects that these group elements act on?
Yes.
The smallest representations, and these are complex representations, by the way, the smallest representations are the identity representation. We always know that. That's one-dimensional. And then the next smallest turns out to be 196,883 dimensional. And then the next smallest turns out to be 212,96876. Okay? So 21,296,876. Those are the three smallest. Okay? So you can imagine if you wanted to write down one element of the monster group in this representation, holy shit. And then there's 10 to the 54 elements of the monster group. So, you need a couple pieces of paper. Okay. Now that's a really cool observation, but here's where the drinking comes in. Okay? The drinking comes in if we consider this seemingly unrelated story. Imagine taking the complex plane. So tau is a complex number. This is the real axis. This is the imaginary axis. And I want to take the upper half of the complex plane. So H is any tau where the imaginary part of tau is positive. Okay? So I want to take the complex plane, this region, and I want to map it to the surface of the Riemann sphere. So for those of you who are coming back late, the smallest dimensional representations of the monster group are 196,883, and 21,296,876. And now we switched gears. We said, we're going to drink. So we're going to consider mapping the upper half of the complex plane to the surface of the Riemann sphere. Okay? Where you can think of the Riemann sphere, we call it C twiddle, is essentially the union of the complex plane with infinity. So if you take the complex plane, you can actually map that to a sphere, but the problem with mapping it to a sphere is you can cover the entire sphere except for the North Pole. Because the North Pole you would actually have to bring in infinity. So if we take the whole complex plane and we include infinity, then we can map it to the entire sphere. And to do this mapping, we're going to use a function. I'm going to call it j of tau, okay? And this function j of tau is, it turns out, if we choose it to be an elliptic modular function, okay, these words have technical meaning, then the Laurent expansion, does everybody know what that is?
Yes, of course.
Who took complex analysis?
Math Phys with Bernard.
Math Phys? Okay, so in complex analysis, you should have seen this. It's essentially the complex version of a Taylor expansion, okay? But if you, listen, here's the kicker. If you expand this function using, instead of tau directly, but the argument q equals e to the 2 pi I tau, then this is what you find for the first few terms in the Laurent expansion of this function j of tau. You find 1 over q plus 744 plus 196,884 times q plus 21,493,760 q squared plus dot dot dot. Okay? I know, but here's the interesting part. All right?
Pascal's triangle somehow?
I switched gears here. This is a line. Below this line has not a thing to do with this. I just decided to quit talking about the monster group.
But you found a number that's almost a number.
Well, what I found was an expansion where this coefficient is exactly this number plus this number. Moreover, this number is exactly the sum of all three. Now, the first two don't matter for technical reasons, but here's the thing. People independently knew this, and then when people started constructing the monster group, they noticed this correspondence, and they said there must be a connection between these two things. They're not related in the way you construct them, but they said there's no friggin' way those numbers can match up.
Yeah.
Nice.
And so they conjectured a relationship. People thought it was so crazy they called it moonshine.
Nice.
And this resulting connection is called monstrous moonshine. And it was speculated and finally proven using the thing that I think is the coolest thing in all of physics. It was finally proven using something called the vertex operator algebra of string theory. Now, string, you all know that I've done string theory, and I think string theory is cool. Emily, stop looking at your watch, and we'll come over there and... You all know that I think string theory is cool, and string theory is interesting. It's got D-branes, it's got extra dimensions, it's got quantum gravity, it's got a lot of really cool stuff. But what I want to tell you is what I think is most fascinating about string theory. Okay? And why, to a certain degree, I would have expected this to be proven with string theory. Okay? When you do quantum field theory, which is based on zero-dimensional particle-like excitation, so when we excite a field in quantum field theory, it looks like a particle, which is zero-dimensional. When you do a quantum field theory you can do quantum field theory in any number of dimensions you want. You can do it in 1 dimension, 2 dimension, 3 dimension, and make that number of dimensions as high as you want. Okay? Shh. In any number of dimensions. If you do gauge quantum field theory, if you have a gauge symmetry, like if you do an SUN gauge theory, you can take this n to be any number you want. So I could write down an SU8 gauge theory in 12 dimensions, and as a quantum field theory, it makes complete sense. Okay?
Yep.
However, in string theory, the only thing you change in string theory, in going from quantum field theory to string theory, is you take 0 and replace it by 1. You take point particles and you make them one-dimensional. That is a really small thing to shift. But what you discover in doing that one shift is that a lot of this changes radically. For example, in string theory, it does not work in any number of dimensions you choose. There are very special cases. We know that there's 10 dimensions, 11 dimension plays an important role, and of course 26 dimensions. The point is that you can't pick any dimension you want. And these numbers are kind of weird, like why 11? Why 26? What happened to 15? Why are you hating on 15? Okay? Moreover, this part of the story changes as well. You can't just pick any gauge group you want. Okay? It turns out that if you have gauge symmetries in string theory, they have to be groups that have either 256 generators or 498 generators.
That's it.
Again, incredibly weird numbers, and you don't have the flexibility that you had in quantum field theory. So the thing that I'm getting at is, the reason I find string theory fascinating, when you do physics, you know, your first job as a physicist is to describe the real world. And if you go out and say the real world's 4-dimensional, then you can say we have no reason to do physics in more than 4 dimensions. That's limiting what you study based on comparing it to the real world. And that's important. I don't want to poo-poo on that. But what I find fascinating about string theory, and the same results in these mathematical contexts, is without trying to limit yourself, you're suddenly running into these limits of what you can do. And so what it means is that, in a sense, string theory is this thing which exists, and you can't arbitrarily change it. Like, you can't take it and just say, I want to do string theory in 100 dimensions. So there's a certain sense in which, just like the monster group, it's kind of out there waiting to be discovered. String theory, as well, is a set of ideas that is complete. We don't completely understand it yet, but it's complete, it's self-contained, and you're not allowed to just generalize it in any way. And to me, that's why it's such a fascinating subject, because it's almost like human creativity has no limits, right? You know, you can always make up new shit. And there's a certain level at which a lot of physics is like that. Like, I can go, I want to do 200-dimensional physics. Oh yeah, I want to do 300-dimensional physics. Well, fuck you, I want to do 500-dimensional physics. But you literally have limits to what happens in string theory. Now, don't get me wrong, creativity is a part, because there's some of the weirdest shit I've ever seen in physics in string theory. But the fact that it's limited is actually the thing that makes it most compelling to me. Right? And that's it. Thanks, you guys.